hopefully I'll remind you at the end of class, but there will be no class on Tuesday in person. I'm going to upload a video, and you guys can respond to it for your Flipgrid next week. So I'll make that link available to you guys, but don't come to class. Somebody's going to, I just know it, but I'll send an email too, hopefully. I need to go to Minnesota. Yeah, it should be nice and cold up there. Yeah. So, and maybe I'll share my talk with you guys too if anybody's interested. It's going to be pretty short. I'm flying. That'll be interesting too, because I'm flying on Saturday, and we're supposed to have a snowstorm. So that'll be super exciting. Nothing like flying in bad weather. You been to that airport? I have not flown out of it, but I've been there a bunch. Yeah, my wife's flown out of it. It's pretty chill, from what I understand.
It's big. It's always windy. Like
yeah.
Step out of that place. Straight line winds.
Yep.
Yeah.
So that'll be interesting. It'll be fun, I'm sure. Yes.
The project and the creativity.
Yes. 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 It's the Saturday right before finals. Yeah. So no class finals week now. So we're really getting close to the finish line here. So we'll have there'll be this virtual class on Tuesday. We'll have class Thursday, and then we have one more week after that, I believe, of classes. No, I think it's due 16th.
Yes, 16th. I was like, wait.
Yeah. So I am going to also be leaving town for a couple months starting on the 16th. So if you want to interact with me at all, these last 2 weeks are the last chance to do it. If you want to, it'll be more difficult for me once finals have started because I will not be around. So make sure you get all your questions answered ahead of time. That's, in another sense, that's why things are all due ahead of, there. Plus, I don't want you guys to be worrying about this class during finals. I'm sure you have plenty of other stressful things to deal with. Cool? All right. Let's try to get back up to speed on what we were talking about last time. Let's see who is here with us today. We're gonna spend more and more time today and tomorrow talking about the lives and deaths of galaxies. So we'll get more into that. The thing about the black holes is kind of interesting. So, and I'll read you this little interesting. I found this little blurb on Wikipedia that sort of tells the story of the standard story for really the universe, but galaxies in general. And it sort of does end up with everything getting eaten by a black hole in the standard story, but it doesn't really make sense because there's all these young stars forming around the center of our galaxy and other galaxies too. And so how's that even really reconciled with these super hungry anomalies at the center? Yeah, I mean, again, remember, like, these are some of the least understood phenomena in the whole universe as far as we know, right? We don't totally understand what's going on at the center of these galaxies. And so, well, next week, we're going to be talking about these active galactic nuclei, which are essentially these galaxies that are just shining incredibly bright light out of the center of them. And again, it's a very confounding situation where, well, the only thing we can think of that could do that is some sort of breakdown of physics, right? So we put these supermassive black holes there. In some sense, I think we can think about them as placeholders until we understand what's actually going on. So yeah, that is interesting. You have something? Yeah.
I was just curious on a side note, like, how do scientists get their theories out there in a reasonable amount of time before the internet?
That's a really good question. Yeah, I had a really wonderful podcast yesterday with this lady who studies the Renaissance, essentially, which is where we think of the birth of free thought and all of this, right, in some sense. And a huge component of the early science after the Renaissance was letter writing, actually. So the printing press was invented, of course, which was kind of like as crazy as the internet being invented in our time. And so people could write a letter and print many copies of it and send it to lots of people. And so that pattern essentially led up to this idea that we have now of scientific journals, essentially. So before the internet, scientific journals were everything. A university would buy a subscription to a journal. It would come out every month or so, and it would have all of the letters in it, right? All of the research articles, we'd call them now. And so, actually pretty long ago, these societies popped up, like the Royal Society, the National Academy, things like this. And they would publish notes, which were essentially the best of the letters, right? So there was a huge tradition of letter writing that went into it beforehand. But yeah, it's really strange to imagine. Like, I don't think that there was the same level of, in science today, it's like there's this idea of consensus, right? This idea that like we're all on the same page about whatever it is, I don't think that was so much a thing back then. I think there was a multiplicity of ideas. There was like, well, did you see this letter by this guy? Oh, no. Like, there's this better letter by this guy, and he can explain the theory a little bit better. And so I think that, my sense is that it was a more fertile climate, actually, for science, because there was a lot of ideas on the table being discussed simultaneously. Whereas today, you kind of have to fit into some paradigm. There's like, if you look at these calls for grants by the NSF or NIH, it's like, we're funding these topics this year. And so you're like, well, how can I fit my idea into this topic, right? And so something kind of sinister happened after World War II when essentially the governments for the first time started throwing a lot of money at science, and it became a career. It was never really a career. So the people back after the Renaissance, they were doing other stuff, right? They were doctors, lawyers, shoemakers, like everything. It was just a thing. It was almost like a dignified hobby for people, right? It was like, yeah, you do your job, but like if you want to be like, really engaging with the world, then you get into natural philosophy and you kind of start participating in that. It's kind of like a club a little bit.
It would be hard. You'd have to be as good a writer as you were a scientist to compel people to really
Yeah.
theory.
Yeah.
You might have other people that were better at writing, not as good as science, but selling their point. That'd be really complicated.
Yeah, people were so good at writing and talking. Like, it's really wild. Even if you watch like interviews and stuff from, at least from metropolitan people from the even 1920s and stuff, it's just incredible how eloquent people were. There's a real danger. I've seen some interesting articles in recent times about how the threat of ChatGPT and so forth is going to make people essentially illiterate because, you can just have the computer even autocorrect on spelling. Like, I guess there was some survey recently, and I can't remember the numbers, but basically, kids today can't spell. That's what that was the kind of headline. So it's interesting. A lot of it is, at every generation, like the old people are always like, the kids are just failing, and of course the kids are going to come up with new technologies and new ways of communicating, and YouTube is one of the most information dense places in the world that's ever existed, right? And so it's more of an evolution, I think, than anything, but yeah, different times. You had to be really good at writing. Getting good at writing, though, I think is always going to be valuable because writing is the best way to organize your ideas. It's like how you learn how to take, even if you just want to develop some idea you have, it's like write it down, read it. Does it make sense? See if you can move things around so it makes more sense. And then by doing that, you'll understand your own idea better and you can communicate it. However, even if you end up making YouTube videos about it, you should write it down first, make an outline, So yeah, they're all really good writers. So that's no joke, for sure. All right, who else is here? Really far away, really unbelievably far away. So going there is completely out of question. Going outside of our own solar system has taken since the 70s. We sent a probe in the 70s that just got outside of the solar system. And it is thousands of solar systems away from here. So going there seems to be improbable. It's interesting, like you bring up that word proof, and I think that's kind of the interesting piece of the puzzle here. No, it's okay. I think that word's like an interesting word that gets thrown around a lot in science and astrophysics, and it's like, as far as I can tell, proof has like two meanings that are really interesting. One is in the mathematical sense, which is an if-then statement. So it's like, if I plug A into this equation, then B is the case. And so it's like this logical deduction. And so math has proofs, and you can trust the mathematical proofs as long as nobody's breaking the rules of math, then you can be sure that the quantities that you get as the output are true. And that seems to be a really valid answer. The other idea is like a trial, right? It's like, did you prove beyond a shadow of a doubt that this person was the killer, right? And as we know, tragically, those kind of proofs, it don't work out all the time, right? It's I don't know if you guys have been following the Innocence Project or really just the advent of molecular and DNA testing. The advances have overturned thousands of verdicts from the 80s when, you were convicting all these people based on garbage evidence, really. Hearsay, a lot of hearsay, like things like blood splatter that were just completely unreliable. You get somebody who's like an expert, but like they don't actually know what's going on. And even the DNA testing, as soon as DNA came out, it was like, okay, you have to have DNA to convict someone. But it was really terrible. Like people just weren't, the technology wasn't there, I guess is a good way to put it. It wasn't there. So when people talk about proving things in science, they're actually kind of talking about more the jury trial type of thing, where they're like, look, the jury has been convinced that this is the case. So because math is really just quantitative logic, and it depends on the assumptions that you go into it. So you can make a mathematical model in science, but it's completely dependent on the validity of the assumptions in it. For instance, if you believe that it's valid that physics can just stop working sometimes, like that's a metaphysical assumption, and it's at the heart of black hole science, right? Like if your metaphysical assumption is that physics holds in the universe all the time, then there's no way you would entertain the idea that it just doesn't work sometimes. And so, no matter what math comes downstream of that, if the assumption is garbage, then you just get garbage output from it. In terms of convincing the jury of things, it does seem like over the past 50 years that the astrophysical community has been convinced of the existence of these physics breaking down and so forth. But in some sense, that's also a metaphysical assumption at the beginning as well. So, one thing I've tried to do with this class is present some different options for what could be going on that don't necessarily involve breaking physics and so forth. It is worth pointing out that astrophysics is almost entirely dominated by mathematicians at this point, right? It's not the kind of physicists that are doing experiments in labs and so forth, right? These are people who are looking at light in the sky and interpreting it based on their mathematical theories. So it's subject for sure to fractures in both of those types of proofs, based on assumptions and based on convincing a jury of people who are all on the same page about their assumptions. So the word proof is really, I try to avoid using it in science because I think it's dangerous. Just like proving somebody killed somebody is also really dangerous, unless you saw them do it, right? Now, there is science where we see them do it, that for sure, right? And honestly, a lot of the basic biological, chemical science that we do in laboratories is we saw them do it kind of science, where it's like we have a test tube, we keep this one controlled, don't put any chemicals in it, we put the chemicals in this one and we see the difference, and we're like, okay, well, this is what's happening. That's a very, very different situation than we have in astronomy, where we're literally just looking at still frames from a movie that's been playing for billions of years and trying to piece together a story. So when anybody says we've proved this about the story of the universe or whatever, I'm always a little bit like, no, you didn't. Like, you might have a really compelling story and you might be right, but it's not a proof for sure. So I know that's a little beyond what you were mentioning, but I think it's always worth taking the time to talk about that word.
I really like your idea about the black hole, because it seems like when we started, we thought we were the center of everything. And the more we learned, we saw the sun was the center of everything, and our view got larger. And now we have this concept of these black holes that we don't understand, but we think they're the center of something. And it's almost like we can't see the big enough picture to put that into perspective. But in the back of all those theories, they're saying it's probably, and it seems like the more we learn, the smaller we get.
Yeah, I think people.
Every time we make a discovery, we're like, and that's in the middle.
Yeah, it's the magical parts in the middle, kind of, right? And humans are close to it because we understand this magic, Sorry, it's really cold up here. I just think that humans we have a sense that there's something magical going on here. And I think that's reasonable. Like, it's freaking crazy that a bunch of atoms got together and sat together in this classroom to talk about the stars. Like, I think that's pretty magical, first of all. But the problem is I don't think that that's a physical kind of magic, right? It's like what's happening in this room is probably not best understood at the atomic level, right? It's like we're having these like high-level abstracted interactions as these agglomerations of atoms that are incredibly organized and complex. We have personalities and hopes and dreams and desires and all this stuff, and it's like, well, that's a lot of magic, but it's not in physics, unfortunately. And so for some reason, physics has made its way to be the king of the academic castle. Most scientists have a little bit of physics envy. Like, they look up to the physicists, like, you guys know what's going on. And so I think we really want to displace that magic onto the physicists. There's something just inherent about hoping that if these guys are the king of the intellectual castle, well, maybe they can tell us about this magic that we all know is real, because we're all experiencing magic in our lives on a daily basis. And like by magic, I don't necessarily mean supernatural. I just mean things that are kind of beyond the basic reductionist explanations that we would hope for in science, you know? So they persist, and I think they persist in a lot of these really tantalizing concepts that capture the public imagination, like black holes and wormholes and dark matter and these things where it's like, well, maybe physical reality itself is magical too. That would be wonderful because that's congruent with the way my life goes in some sense. All right. Let's get like one more, maybe two more people here. Yeah, that was when I read that, when I realized that's what was going on, that was one of the first moments where I was like, I don't know if you guys know what's going on here totally. You know, I really uphold the motto of, I believe it was Carl Sagan, no, it was Feynman actually, who was like, look, science should be a discipline of skepticism. Like when you hear a theory, your job as a scientist is to be like, right? I mean, you're kind of a little bit of a grouch, you know, that's part of the job of the scientist. Because the opposite of that is essentially just faith, where it's like somebody says something and you're like, yeah, sure. And so we have to be skeptical. And that idea that you mentioned, the infinite density in a zero volume, should, you know, perk up your ears a little bit. That maybe instead of these being extraordinary events where physics break down, they're extraordinary events we have no idea what's going on there actually. And so I think that's probably the more reasonable interpretation. Actually, that point of infinite density and zero volume is called the singularity, right? Which in every other science, when you have these infinities occur in your equations, you just realize that that is where your theory stops working and you don't try to apply it beyond those boundary conditions. But for some reason in astrophysics, it's part of the theory. You never see that anywhere else in science, which is very, very bizarre. So. Yeah, and of course, this idea is enabled by several key, you know, in my opinion, like several key mistakes, which is that A, you're treating large bodies as if they're points with masses, like that's a nightmare by itself. B, you're treating stars as if they're ideal gases, and so of course you can squish an ideal gas down as far as you want. As long as they have no material structure, then these theories, these mathematical laws can be applied to these extremes and you end up with these supernatural features. But I don't know. I just think that 1,000 years from now, people are going to think we're a little bit medieval, honestly. But that's how it goes. That's how we look back. And of course, there was brilliant people in the Middle Ages who were coming up with really smart ideas that didn't surface for 1,000 years later. What's that? Yeah, it's really interesting. Yeah, the attempt to remove God from the equation across the years has been really interesting. You know, actually Newton, who's probably like the biggest hero of physics or just of science in general, probably I would say. I mean, Newton was, if you read his magnum opus, the Principia, he basically says that, he gives his famous laws for gravitation, right? This is the ones we've talked about in the course with mass of bodies being important and the inverse square of the distance describing really the forces between these bodies. And then at the end of it, he's like, but, in summary, he basically says, but, only God would know why the bodies are attracted to each other. It's not the job of the natural philosopher to give cause for these events. We just sort of describe how it happens mathematically. And what's interesting is there's another guy on the other side of the water, right, over in the continental Europe, this guy named René Descartes. And Descartes was like, no. We have to at least, even if we can't see what's holding the bodies to each other, something must be there. It's just inconceivable that two bodies would orbit each other without being attached somehow. And so he had this vortex ether model for how it worked. And, Newton attacked the heck out of Descartes in his magnum opus, and he came up with all these reasons, particularly involving comets, why that wouldn't work out. Many of which turned out to not be true, because comets, it turned out, actually obeyed gravitational dynamics. They were just on these really large elliptical long period tracks, right? They didn't know that at the day. They would see these comets come in and leave, and they were like, oh, they're not orbiting anything. So his vortex model was thrown away, but it's really just a matter of where you put that uncertainty. This is what I've come to realize is Newton is like, well, we're not going to introduce any hypothetical actors because that's sketchy. And instead, we'll just put the uncertainty in that we don't know the cause of things. And Descartes is like, you have to at least propose some cause of things, even if you have hypothetical actors. So he wanted the uncertainty at the stage of the hypothesis, whereas Newton just wanted to have really tight mathematical descriptions and just be like, God did it, right? And actually, the kind of physics that we have today that allows for black holes and things like that is very much the Newtonian kind that says, this is the mathematics of the situation. I don't know how it happens, just it does like this. And so, it's often the popularizers, the people who write newspaper articles, make Hollywood movies that really bring out the worst in the mathematical physicists, because they're like, hey, do you think that, what would happen in a black hole, and then it's just kind of off to the races. So yeah, cool, really interesting stuff there. It'll be, and I'm not sure there's an easy solution set there too, except I really do look back to those early days of letter writing where there's a lot of people with a lot of different theories and a really wide open, liberal, democratic discussion of ideas, like a real marketplace of ideas where there's a lot of competing theories. And I'm worried right now, well, I have been worried that the narratives get too constrained in the modern publishing landscape. But I don't know, after talking to this lady yesterday about the Renaissance, it's interesting because when they did the printing press, all of the governments also tried to really control what was printed, right? Kind of like YouTube, right? They won't let you talk about certain things on YouTube. But it didn't work out, right? People found ways around it. People started, they had to get this stamp on your book when you published a book at the beginning from the king, basically, like a royal stamp of approval. But people were figured out how to forge those in no time, essentially. And, the printing press really quickly led to this proliferation of free thought and people being able to correspond about things that they never would have in the past. So, I don't know. I think we'll be all right, I guess is where I'm going with this. Okay, let's move on. So I want to talk about galaxies a bit more today. We'll talk about the center, this mystery at the center of galaxies next time a bit more. I want to talk about the different types of galaxies, and I want to work towards, we're going to crack open some cosmological ideas today, at least with respect to this expansion idea. So I want to interrogate that concept, which is so central to modern cosmology, and give you guys an idea of where that came from. I thought I'd maybe start by, I just found this quote this morning on Wikipedia. I was just reading about, Wikipedia is an interesting thing. It's about 90% true, right? So it's it's a good overview for the climate of some very mainstream perspective on any given topic, And if you want to go deeper, you can always go to the talk pages of Wikipedia and see what people are arguing about and so forth. But the way that they summarize the life and death of a galaxy is something like this, and I think it's interesting. So the idea is basically that all the galaxies that are in existence were all formed at the same time, right after the birth of the universe, and there's really been no churn. And so the story goes like this. The current era of star formation is expected to continue for up to 100 billion years, and then the stellar age will wind down after about 10 trillion to 100 trillion years as the smallest, longest-lived stars in the visible universe begin to fade. At the end of the stellar age, galaxies will be composed of compact objects like brown dwarfs, white dwarfs, and cooling cold black dwarfs, neutron stars, or black holes. Eventually, as a result of gravitational relaxation, all stars will either fall into the supermassive black holes or be flung into intergalactic space as a result of collisions. So there's this real like doom and gloom narrative that we have sort of packed behind the story of our universe right now. And I thought that would be just a good preface because it's kind of in the liner notes of everything that we're going to be talking about in the next couple of weeks. But I think that this narrative, like, and I think we'll see that it's not as well defended as it might appear on the surface. I do think that it's in some sense subject to the confirmation bias that we have as human beings, right? I mean, we certainly all live, we all die, and that's probably our biggest crisis, is that we're all going to die, or at least the people that you love are going to die. That's maybe a better way of looking at it. But it doesn't seem outrageous that we would try to frame the entirety of the universe in those same boundaries, let's say. So the basic formation model, this is where we stopped last time, was this old Kantian idea that you have a nebula that collapses and starts swirling around, and that's how you get these spiral-shaped nebula. And actually, Kant was the first guy to say, I think those might be other galaxies. And Kant was a philosopher and not a scientist, so nobody took him seriously per se. And that idea was actually not really adopted into science until the 1920s. We talked about that a bit last time. So in addition to this basic formation model that we've talked about, this is called the monolithic collapse model, which is shown here on the screen. And it's sort of like the figure skater contracting, and beginning to spin and so forth. But in addition to this, there's this idea that galaxies can merge often too. And this seems to be playing out in various parts of the sky. And as we've gotten better and better telescopes, we've been able to see these merger events happening and perhaps having happened in the past. So it turns out that there's really only a couple of shapes that galaxies take. Well, there's some diversity, but most of them are either these spiral-shaped, which conform to this Kantian idea, this figure skater spinning collapse thing, or they're these big balls, right? These big kind of nebulous balls. And the idea is that the big nebulous balls are actually the result of mergers of several of these spirals. And so they're going to be the older galaxies as we move through this story. So the idea is that there's oftentimes much smaller little galaxies that will begin to orbit the bigger spiral galaxies. And they'll start to tug on the arms of the galaxy, and they'll start to rip off some of the gas and some of the stars from the main galaxy. And we actually see this in our own galaxy. There's a number of little satellite galaxies that we have. I'll show you, like here, this is a good, this one's called the globular cluster M54. This is a picture from the Hubble telescope. It's now, thought to have essentially ripped off little pieces of our own Milky Way along the way. And to that end, we have a galaxy rushing towards us right now, actually. So how do you know that something's coming towards you? We've talked about this before. The color, yeah, the red shifting, right? The blue shifting is actually coming towards you. So one of the nearest, fully formed spiral galaxies to us is called Andromeda. We talked about Andromeda in the mythology section. Andromeda is rushing towards us. She has a high blue shift, actually. So what's going to happen? It's going to be kind of interesting. I don't know if I believe this is from your textbook. It could have been from somewhere else. Yeah, looks like it's from your textbook. The idea is that when Andromeda slams into our galaxy, that we'll end up with a much more globular-looking galaxy at the end of the day. And the idea is that, let me see if I can get the timelines here. So 3 billion years from now, this is in the first frame here, 3.75 billion years, Andromeda has approached the Milky Way to the point that we can actually see her brightly in the sky, coming in hot. Then there's going to be, as they collide, there's going to be a bunch of new star formation, is the thought, which continues for, up to 3.9 billion years. The galaxies then begin to change shape with each other. Andromeda gets stretched out, ours gets warped. This is only 4 billion years from now, which is crazy because life on Earth's only been here for 3 billion years, right? It's not that long, actually. So, and then 5.1 billion years, the cores of the galaxies become these bright lobes that overlap. And then after 7 billion years, the merged galaxies form a huge elliptical galaxy whose brightness fills the entire night sky. So that's pretty crazy. Of course, this is all just, it's completely hypothetical, right? We have no idea what's going to happen. So we do see galaxies in various stages of what we believe are mergers, but we don't really understand the interactions, right? If you think back to our brief discussion of this dark matter crisis, right? There appears to be a lot of stuff in the arms of outside beyond the sort of bright part of the galaxy that's pulling on the arms, right? Now, whether that is some magical fluid called dark matter, or whether it is just a bunch of old, cold, dead stuff, or whether gravity is not the main player at the scale of the galaxy. Maybe there's friction or electromagnetic forces that we just don't understand. All those things are going to change how this story plays out, right? And it might be that galaxies interact in ways we can't even think of, right? That we just don't recognize because they're less catastrophic, let's say. There might be more do-si-doing and swinging and just, interactions that are hard for us to picture. So this might happen, this might not happen. None of us are going to be here to find out. But it seems like this idea that environmental influences, and not just the galaxy's original characteristics, are playing more and more into the way that people are conceiving of galaxies taking their shape. Now, it's probably a good point to stop and say that there's absolutely no agreed upon way that galaxies evolve and take their shape. It's just, nobody knows. These processes play out over far too long. And, a huge consequence of this Big Bang discussion right now, so if the Big Bang model falls and we have a much longer time for a lot of these events to unfold, I think that it'll really open up an evolutionary discussion, much like we've been having with the stars, right? The stars have these long, they look like one type of star, and then later they look like a different type of star as they exhaust their fuel. I think we might start at that point to reimagine some of these, dwarf galaxies maybe as the earlier stages or the later stages, I don't know, of galaxies, right? We might start to actually put together a timeline because we'd have to explain that new galaxies are coming into existence all the time. Now, the biggest trouble with the story that all the galaxies today are the ones that formed at the beginning of the universe is that the new James Webb Telescope has been able to see galaxies that are almost as old as the universe itself. And I'm talking about galaxies that are only 200 million years older than the universe, as the universe is given a birthday right now. Problem with that is that those galaxies look almost identical to these fully formed galaxies like the one we're sitting in right now. So why in the world were there fully formed galaxies 200 million years after the birth of the universe? It's a little bit troubling, right? The obvious answer is that wasn't the birth of the universe, and that galaxies are getting created all the time, and we're perhaps not looking at these things the right way. So that's kind of the way I expect it to go in the next century or so. But these huge meta-narratives die painful, slow deaths, so we'll see what happens. And I'm going to poke some more holes in that theory as we go ahead. I really want you guys to understand the lines of reasoning that have led people to believe that. So we'll make sense of that today. I think we'll talk about the Hubble expansion and the Redshift a bit. But there's really only two solid pieces that are pointed to defend this idea that the universe has a birthday. One of them is this redshift that we'll talk about by the end today, and the other one is the cosmic microwave background, which we'll deal with next week. And both of those are a little bit troublesome. You know, I don't know if I'd send a man away to his death based on either one of those pieces of evidence. All right. What else? So we talked about this already, that people, of course, started to realize that galaxies, that we weren't the only galaxy. I'm not going to beat that horse anymore. Now, this is Hubble's classification scheme. Now, Hubble was, of course, this very famous astronomer back in the early 1900s. And he kind of imagined that the ellipticals were, in some sense, developing into the spiral galaxies. That might be true, but this isn't the way that people think about galaxies today, although the classification scheme, of course, still remains, right? We still have this same numbering scheme for the galaxies, although today it's actually thought that these elliptical galaxies are more the mashup. The more popular theory, anyways, is that elliptical galaxies form when spirals smash into each other. And we'll see why people think that, but it has to do with the ages of the stars and the fact that ellipticals seem to have used up all of their gas and dust in a way that the spirals seem to have plenty of it still, so that people think they're younger. Ellipticals are just kind of a ball of stuff. Okay. Yeah, which is maybe not the best name for them, but yeah, you can have sort of flattened ellipticals, you can have more rounded ellipticals for sure. And then you have two different types of spirals too. The two different types of spirals, I'll get into those a little bit later, but you obviously have one with... Yeah. So there's these ones that have like a bar connecting them, right? And poorly understood. We'll talk about the bars a little bit later. So obviously the spirals are our favorites because we live in one. and they're also just super cool looking, of course. Andromeda is also a spiral too, which is this really one of the most easy to view galaxies, of course, formerly thought of as a spiral nebula. Actually, there's not too much to say about the bars, the more that I think about it. It seems like more massive galaxies have bigger bars than less massive ones, but that's not particularly interesting. The formation models for these things is pretty vague. So there's like some speculation that when the stellar orbits in a galaxy become unstable, they deviate from their circular path, so they start tugging on each other in one axis for some reason. But that's a very hand-wavy explanation for why these bars form. It's like instabilities build up or something, which is like rather vague. I don't honestly think that anybody has any idea. There's probably somebody defending this mathematically in some sense, but it may tie into also some of these other huge mysteries, right? Like we'll get into next week, the active galactic nuclei. That's a hard one to say. Active galactic nuclei, right? These huge jets that are shooting out of galaxies. Well, they're not doing it in every galaxy. What's happening? I don't think we have a good sense of how galaxies evolve across time because the paradigm we've been operating under is that, well, they only formed once, and we're sitting in one, and they're all basically the same. And so it's not an ongoing process that we need to concern ourselves with, like star birth and death, right? But I personally think that's probably, that's going to be a big change happening soon. So the ellipticals, these ellipticals are mostly old stars. They're sort of spheroidal, actually. The light's kind of dominated by this reddish color, right? These are population 2 stars. They've burned through everything. Dust emissions, gases, ionized gases don't seem to be as conspicuous in these galaxies. You don't have as much of that, which lends credence to the idea that they're older and used up in some sense. Now, there are some other interesting galaxies that don't fit into these two populations, which I think these are probably going to be the real players in the future theory of galaxy formation, because there's these weird ones, irregulars, and you can see a couple of these irregulars really easily, actually, in the night sky if you know what you're looking for. Next to the Milky Way, we have this Large Magellanic Cloud and Small Magellanic Cloud. These are both irregular galaxies. And they're interesting because they seem to have a good mix of young and old stars and gas and all the stuff that we would have in a regular galaxy. They just don't have the fully formed spiral shape yet, which is really interesting. And they're kind of tiny. So, the idea is maybe in some sense, some of these irregular galaxies could collaborate to form maybe a big enough agglomeration at some point. Maybe they will rip off chunks of the Milky Way at some points. Maybe they can steal some of our gas and dust. An interesting thing about them is they seem to trail a bunch of gas and dust behind them, almost like comets or something. So in some sense, they seem a little bit inchoate. They seem kind of youngish, right? They seem like something's forming or happening in these irregular galaxies. And as far as I can tell, there's no real evolutionary model for these galaxies' shape. So they're a big question mark, and I think they could play really heavily into the future story of how galaxies take their shape. Again, nobody's been working on the contemporary formation of new galaxies in the universe because people don't think that happened ever. But I don't think that's going to be tenable going forward, especially having seen these fully formed galaxies, at the very earliest days of the supposed birth of the universe. Doesn't make sense. So everyone knows it doesn't make sense too. It's a really, really interesting moment in history. So how do we measure the mass of a galaxy? This is kind of interesting. So the way that we measure the mass of a galaxy is basically the same way that we do with the mass of a star. We look at how fast the outer bright parts are going with respect to the center. And then we use basically Kepler's laws to discern how much mass is inside of that orbit. And it's an interesting method to judge the mass of something because we know that in our own galaxy that the mass doesn't actually specify the rotation dynamics of the bodies themselves. And so back calculating the mass from the rotation dynamics seems like it would be a complete failure of a method. But it's what we do, and it gives us some approximate notion of the mass of these things. So what did I want to say about this? What's really interesting is you can see that, we generally think about these elliptical galaxies as being agglomerations, right? The story is that they're mashups of spiral galaxies, but the masses aren't significantly different between them, right? Same with the irregulars, right? They seem to, in some sense, have as much mass as anybody else. I guess the ellipticals do have the most. Like they go as high as 10 to the 13th solar masses, right? So, okay, I guess I could see them being, in some sense, mashups. But the irregulars seem to have just as much, almost as much mass as anybody else. So put a couple of irregulars together and you might be able to make a galaxy. I don't know. It's an interesting idea anyways. Let's see, what else do we have to say about this? Let's keep going. So in terms of, one of the big things we're working towards is constructing this map of how far away things are. This turns out to be really important when putting together this cosmological story of the birth of the universe because we need to know that things that are this far away are moving with this speed. So in terms of calculating the size, we've talked about, or the distance, we talked about a few methods, right? We talked about using parallax to calculate the distance of things that are pretty close by, right? That we can really, really nearby stuff, especially using these eclipsing binaries and so forth, and setting up this triangle with the baseline. That works for things that are really nearby. Then we had the Cepheids, right? So there's these stars that blink with a particular known rhythm. And so we know how big those stars are based on them being of a particular breed of stars. And so if something far away is blinking like that, we think, well, based on its apparent brightness, we can say how bright it really is, and then we can deduce how far away it is. there's also this idea of using supernovas, right? So here's a cool picture of a supernova. Let's see, where is this thing? I don't know which galaxy this is, but you can see that the supernovas in the bottom left-hand corner is almost as bright as that entire galaxy there, right? Now, supernovas like this, these type 1 supernovas, they have that particular curve, right? So if you think, well, we know how, again, just like the Cepheids, we know that this is this one type of supernova, and we know how bright it seems to be, and we know how bright it truly is, then we can deduce how far away it is as a result of it. So that can get you pretty far. So you kind of get a sense here for the different scales of how far we get out. And the supernovas will only take us so far, right? They'll take us about, 11,000 million light years, so 11 billion light years. Well, we can get on supernova data, which is pretty good. But there's a fair amount beyond that, right, that we can't get to, which is where we have to turn to this redshift concept, which is what I want to spend a good deal of time on today. So this whole idea is summed up in this thing called the distance ladder. And in some sense, what's really interesting is that the parallax is really the only direct measurement of distance that we have. So much like we were talking at the beginning of class about making proofs for something, the best kind of scientific proofs you can do are in a test tube, where you can literally add a chemical to one tube and not to the other. And you can say that the effect you observed was the result of adding the chemical to the tube. The next best thing you can do is make a direct observation of nature, right? You see a snake eating a rat, and you say snakes eat rats. Okay, fair enough, right? So the snake eating the rat observation, all we have is parallax for that. So everything after that is starting to be based on theoretical assumptions about what we're looking at is. In other words, when we move into the Cepheid variables and so forth, we're starting to make these conclusions that what we're seeing is definitely the same type of star that we've seen in our local neighborhood. It's behaving the same way, its pulsation is the same, and therefore it's as bright as we think it is. Now, that's a huge set of assumptions. And actually, people were using Cepheids for several decades before this guy named Walter Beatty came along and discovered that the Cepheids that they used nearby to calibrate their standard candles were actually very different than the ones that they were using to measure distances to nearby galaxies. So there was two types of Cepheids. He discovered that we were actually confusing the two. This turned out to actually change the distance by a factor of 2x. So that just happened one day, right? And so all of these, the further and further we get away, all of these different candles that we use, they're really based on the back of believing that our theoretical understanding of what they are is correct. And so those things could change radically in the future. And I think that's really worth being aware of as we move into the next stage of cosmological discussion, where we're talking about the overall structure of the universe, right? It's built on the back of a lot of other theories that honestly, at least in quantitative, if not completely in qualitative terms, could radically change at any moment if somebody realizes that our candle is actually 3 different types of candles or 5 different types of candles. It's happened before, so that's worth taking a note of. Now, we're not going to get into all these different ones, but essentially, people are looking at these objects, radio jets, masers, type 1 supernova, that's one that we've talked about, and assuming that what we see in these other galaxies is the same type of supernova with the same brightness curve that we see in our galaxy. And it's a reasonable assumption because the time decay curves do seem like you could make them congruent, and some of the spectral overlap is similar. But they're huge, huge assumptions at the same time. So this distance ladder is the best we can do, but it's by no means the end of the story. Again, I think astronomy is probably one of the most difficult sciences to say anything definite about. I hope that you guys understand that. It's like no other science that I can think of do we only have light to look at, right? We're just staring at the sky. And we have incredibly sensitive instruments, right? We have radar telescopes, we have interferometers and infrared telescopes. We can look at all the different types of light, but that's all we got is light, too, at the end of the day. And what is light? That underpins a lot of this as well. Well, we have really good mathematical theories to describe how light behaves, but what is it? What is really going on? What's the atom really doing to another atom? And we might have to answer those questions before we can really have a ton of confidence in our ability to estimate even questions like distances, what's going on. How does light actually, what is it like having light go through a vacuum of space for hundreds of or if not millions of light years in between galaxies, right? What happens in there? We don't know. So here's a quote from your textbook. "We now come to one of the most important discoveries ever made in astronomy, the fact that the universe is expanding." Okay, but what is a fact exactly is a great question, right? So we have to pause here and tell a little bit of a story about how this became a fact in astronomy, and why it's on the ropes again today. Why it's about, why some people are saying it should lose its fact status. So, when they first started doing spectroscopy and looking at these, when they first started to realize that these other spiral nebulae were galaxies, they did the spectroscopy on them. And a lot of this work was done by this guy named Vestos Slipher, which is an interesting name. And he noticed that these distant galaxies had very similar spectral components to much of the stars in our own galaxy, except that all of those frequencies were tilted a bit towards the red for these different galaxies, these farther away galaxies. Not all of them, though, right? So a few galaxies, like Andromeda, Triangulum, M81, basically our close neighbors, seem to be kind of rushing towards us. But the ones that were really far away seem to be moving away from us. Now, the initial thought was, okay, well, something must happen to light as it travels across these extraordinary distances. This was really the most common wisdom of the day was, well, clearly light behaves differently when it travels across trillions of eons of space, right? It's just, something is going on. Now, of course, it's very easy to explain because, I don't know if you guys will recall this, but the energy of light, in some sense, is proportional, like how much effort you put into, say, a light bulb, right, or into a flame is going to change the frequency of the light, right? So really, really powerful light is going to be more on the blue side of things, and the kind of weaker light, you can think about radio waves as being some of the weakest light in terms of energetics, really long red wavelengths, right? I like to think of radio waves as red, like the deepest red imaginable, actually. Like you can't even see them, they're so red, essentially. So it was kind of, everybody was just like, well, yeah, like the light loses energy as it travels across these vast swaths of space. And that was fairly well established. I think that was the common knowledge of the day. And then this guy came along. So this guy, he's a priest, actually, Belgian priest, which I don't think is insignificant. Mathematician, not an astronomer. So this Belgian priest and mathematician. And what he did was he looked at all of this data, which was now being called the Hubble relationship, with distant galaxies having high redshifts. And he realized that what he could do is if he assigned a proper velocity to these redshifts, right? In other words, how fast are these things moving away from us? What he could do is essentially triangulate all those points backwards if he just sort of projected it back in time where all of these things used to be, that they could all converge on a point of infinite density, right? And a perfect moment where everything was born, right? And of course, we're at the center of that, right? It's all converging on us here, right? Now, that might have gone unnoticed. Of course, Einstein's idea of general relativity was becoming very popularized at the time. Actually, Lemaitre was in some sense part of the same crew of people with Eddington who managed to translate this paper into English and actually was able to give it the proper relativistic treatment and show how this moment of infinite density could be entertained under the relativistic equations, right? Now the Pope, as you can imagine, got super excited. It was like, we proved the creation moment, right? And actually there's these letters from Lemaitre and he's like, dude, no, like, shut up, like, don't say that. And so the Pope was like, oh, yeah, like, we shouldn't say that. But of course, as you can imagine, this fit really nicely into all of the pre-existing cosmologies, right? So all of the traditional, if you go back and you look at the creation stories from almost every culture, you look at indigenous cultures, Mesoamerican cultures, ancient Chinese cultures, they all have something like this. The universe hatches from this egg, basically, right? There's this moment where, and of course the Judeo-Christian tradition covers this very, obviously, right? You have this moment where the universe is made, right? It's created. So Lemaitre mathematized that. He made it congruent with the data concerning redshifts, and Eddington and others helped fit that into the Einsteinian relativity that was becoming so popular of the day. And voila, you had the modern Big Bang cosmology born for the first time. Now, when it was born, there was a lot of people holding out. So Einstein himself didn't buy this idea. A lot of people, of course, the scientists across the past 200-300 years had very much set themselves against classical mythology, right? They wanted to be seen as really objective. And so as a result of that, most of the scientists thought that from a physical perspective, the universe was eternal. It had always been here. It was evolving and changing shape, but it was, in some sense, there wasn't this creation story. And so most scientists weren't buying that. It actually didn't really make it into mainstream science as the story for the universe until the 1960s, which is really interesting. And to see how that happened, we're going to have to look at the cosmic microwave background discovery, which is another interesting story that is the other, I think, leg of this monster. Yeah.
One question that led, I don't know, according to relativity, when gravity is more dense, time changes and acts differently, right? So for example, we're in another planet, in another galaxy, time will be different. According to whatever, I don't know, like time like in Jupiter will be different a little bit, and there's those like variations based on gravity. Wouldn't it be foolish to assume that time passed the exact same way and that's singularity moments? Because gravity would have been just so dense that time would have acted differently and not just like linear, per se.
Yeah, that is part of the story, for sure, is the differences in time. I mean, I think that to throw some water on that, the problem is that you have to ask, what do they mean by time, right? And what do they mean by time? Does anybody, I think we talked about this a little bit. Yeah, they mean what clocks do. That's how, right? It's a measurement in their system. And I think it's really worth pointing out, like, take a pendulum clock up to outer space, time stops, right? And you can use a better clock. You can say, well, my atomic clock, it's better. It's more precise. It's like, well, you pull an atom away from all of its other friend atoms next door. I don't know, like, maybe it's not under the same pressures it was on Earth. Maybe it beats faster, because atoms are vibrating, right? Maybe since it doesn't have anybody yanking on it nearby, it vibrates faster. That seems perfectly logical to me. So I think we have to be really, really careful not to reify concepts like time. We can't take an abstraction like time and treat it as if it's a material object. It's not a body. Time is not a thing that you can apply material deformations to. Like, I can't just like take like the feelings of love I have for my wife and warp them, right? Like, that's a physical process. I can't apply physical processes to abstractions. It might be poetic, like it might have some value. It's not a completely vapid statement, but it's not a physical statement. And so we have to be really, really careful with that stuff. And so, yeah, of course, like if you're willing to start treating time as if it's a physical actor, then you end up with all sorts of insane conclusions that are possible at that moment, right? In these singularities and at these points of infinite density, and when all of these things happen. And they're mathematically permissible because the math doesn't care whether something is physical or not. It's just a parameter in the equation, right? So, you know, I mean, I think I'm presenting this perspective because A, it makes sense to me. B, because, you know, I think that your textbook and PBS and everybody else is doing a perfectly good job of presenting the more superstitious angle on all of these things. So I feel like you guys can get that elsewhere. But also, but mainly just because I think that things should be sensible. Like, I think it's a very empowering perspective to understand nature. Like, I think each one of us has the right to understand what's happening in the world around us. And in some sense, the more, as you guys become adults and become fully autonomous, functional humans in the world, all of your strength and power comes from being able to understand the world around you. Like, I think about when I was 18, I had no idea how anything worked in the world at all. It was kind of terrifying in some sense, right? There's a lot of anxiety for me that comes from not knowing how things work. And so someone's just like, well, like, go take, you know, differential equations before you can understand, like, how the formation of the universe worked. I'm kind of like, I don't know about that. Like, I think that we need to have explanations that make sense, right? There needs to be, there's really nothing, there's no reason that any scientific principle can't be explained to my grandmother. Like, one of my first mentors in the first lab I worked in was like, I remember I was presenting like one of my first research projects, and he was like, how would you explain this to your grandma? Like, and he's like, and I was like, geez, I don't know, it's pretty technical stuff. And he's like, you can't explain it to your grandma, you have no idea what you're talking about, basically. And that's the way I feel about a lot of this stuff. And so, you know, it's really easy to obfuscate your lack of understanding behind extraordinarily technical language, mathematics, things like this. And you can sound smart, but the fact of the matter is that you're confused too. And I sense that that's where a lot of this stuff has ended up at this moment, which is fine. We're only 300 years into this scientific project in general. So why should we have everything figured out right now? We shouldn't, you know? People 10,000 years from now are going to understand things way better than us. So I don't think that it's something we should be embarrassed about, but I don't think that we should be under any illusions that we're at the end of knowledge or anything like that either. And I think that the cropping up of these superstitious things inside of the narratives should be a clue as to where the mysteries lie and where we should be going for them. So, you know, one of the interesting features of this redshift relationship is that actually the nearest galaxies, well, the ones that are farthest away actually appear to be moving away faster and faster, right? So this gets us to this other conclusion that was sort of baked in to Lemaitre's findings, which is that the rate of expansion, so the things that are farthest away, speeding up. It's almost as if since the beginning of the universe in Lemaitre's model, the Big Bang, as it was later called, seems to be accelerating over time, right? And so the idea is that things are sort of increasingly rushing away from their origin points. That was the conclusion. It's worth pointing out, though, that like I said, that this wasn't actually a mainstream idea until the 1960s with the CMB. And we'll talk about that soon. I think there was a pretty strong wing of science that liked it, but there was also a lot of holdouts, including Einstein himself. So, you know, it was much more popular for people still at the time to say, wait a second, I think we just don't understand how light loses energy across vast swaths of space. Now, it would be a little, it will be, and it would be, and understanding this is not as simple as just thinking about the speed of light slowing down or something like that, right? So if you think about, if I shine a light into a glass of water, or let's just say a prism, maybe it's easier to think of this way. Certainly, the light has to be, you know, transmitted from atom to atom in the water, and the result of that is that you get, you know, a very simplistic way of saying this is that the speed slows down a little bit. And because the speed slows down a little bit, the different waves actually separate out from one another, you know, because they're all moving, they all have different, they have different energies, each of the waves, and so they're going to interact with the water in different ways. So you spread out the light. Well, the troubling thing about this galactic redshift is that we're not talking about certain waves being affected more than others, like we would in a medium. So it's not as simple as the light is going through a bunch of dust, or it's going through a bunch of opaque neutral hydrogen that's sort of lensing it or something like that, right? It's just losing energy across the board. All of the wavelengths seem to be losing the same amount of energy across the board. And I think that that's why these, what would be called tired light theories, all seem to fail, is that they couldn't come up with a robust mechanism for how it was that all of the light rays were losing energy across these eons. And it's a little bit, it's one of those things that new papers, new tired light proposals come out every year. People are always proposing new ways. The problem with these models is they're all highly mathematical, so probably 10 people can understand what the author is talking about. And moving the needle based on some new mathematical argument is almost impossible. Who knows whether somebody's actually solved this problem by now or not using a tired light model. But needless to say, the CMB in the 1960s really pushed those ideas to the sidelines. And once they had this other big piece of empirical data that they could point to and say was a second piece of evidence for this Big Bang, people sort of stopped looking for alternative explanations for this redshift across the spectrum. So, there are some troubles with it, though, for sure. One of the biggest troubles, this really interesting guy, there's a book written called Seeing Red by this guy. He was one of Hubble's proteges. He worked, numerous posts, NASA and at the big Hubble projects. And his name was Halton Arp. And he got a little obsessed with these anomalies to this redshift data that he started finding everywhere. So he became particularly obsessed with these one phenomena, which turned out to be what we're going to deal with next week, which are these active galactic nuclei. So galaxies, just to preview that, some of them have these jets that are just shooting out this stuff really fast. Now, what Arp noticed, though, which was really troubling, was that sometimes when those jets were pointed directly at us, they had really high redshifts. So there was an intrinsic redshift component that had nothing to do with the direction of the motion of these jets. And he started finding them everywhere. And he found, I don't know, he made catalogs of these. And he was really pissing people off, actually. Because he said, guys, I think that what redshift is, I don't think that we understand what redshift is. I think there's something intrinsic about the way that molecules are interacting as they're, and we'll see these active jets are thought to be sort of primordial material that's maybe assembling into new atoms even. And he thought, well, I think there's something more, there's some sort of atomic processes responsible for this redshift that aren't just related to the motion of things, right? And so, of course, that combined with the fact that there are several of the best studied galaxies that have actually quite blue shifted ranges, they're coming directly towards us. All these things are like serious thorns in the side of the idea that everything is just uniformly moving away from one another. So nobody really knows what's going on with that. I mean, and of course, a huge component, even if people come to the idea that, well, this Big Bang birthday that we have is no longer tenable, say just from galactic formation alone. Like, that doesn't work. The universe has to be older. Nobody really has, there isn't a great consensus model for what's causing this redshift at the moment. And oftentimes new paradigms aren't going to be able to, or say the old ideas that are failing won't be able to be let go of until we have a really solid grasp on what could be causing this sort of phenomenon. So the explanation given for this, of course, this is from your textbook, which I think is a really interesting illustrative point, is of course, Einstein broke up the universe into coordinates, right? So space, which is essentially the distance between objects, right? The distance between bodies is space. It's a coordinate system of measurement, right? And so the Einsteinian interpretation of this expansion due to redshift is literally that the distance between bodies is increasing, right? Now, this is really problematic because, of course, you treat bodies as points, not as actual bodies in relativity, right? And so like your textbook has here, which is like quite illustrative of the crisis, in my opinion, is that you notice like when the space, the ruler expands here, the ants are perfectly fine, right? Which is really bizarre because in relativity, there's no ants, right? There's just space, which is the distance between the ants, right? And so actually Einstein has done such an incredible job of removing material reality from our physical conception of gravity. It's almost astounding, right? Because, you know, you might think, well, if the universe is expanding, wouldn't the ants be expanding too? Wouldn't the Earth be expanding, the galaxy, everything would be expanding, right? And it's like, well, not if the Earth is a point, a dimensionless point responsible for its mass. Not if the galaxy is just a point, right? This is like, in some sense, I'm trying to illustrate to you that there's a real danger of making abstractions, despite how predictively useful they can be, actually. You know, relativity is fantastically predictive if you're trying to set up how your spaceship's going to move or how your GPS is going to be affected by gravitation. It's very, very useful. But it's completely removed material actors from the universe, right? And so, you know, the idea that the distances are expanding seems to be the natural consequence of interpreting this redshift according to relativity alone. So, how can I wrap this down? I mean, what we've done here, I guess, to just put a bow on this, is that you've taken an idea, right, like time, and in this case, you've taken an idea like distance. Distance is actually an abstraction, right? It's a relationship between two material bodies. And you started applying physical processes to an idea, right? Now, philosophers have been aware that this is a fallacy of logic for thousands of years. It's called reification. It's a really important term. I want you guys to try to use that in conversation at some point this week. Whenever you mistake a map for the territory, you're reifying the idea into something concrete, right? You're treating something which is relational as if it is an actual actor to begin with. And I can't think of a better example of reification than what's been done here with the distance being treated as if it's actual material that's being warped. So, in some sense, we're at the end of the road here. We see some very strange stuff. We see very red galaxies that are very far away. We don't really know why that's the case. We could say that it's because they're flying away from us, but then that leads to all sorts of other questions like, why aren't the things nearby us flying away from us, right? We could say that it's because the light's getting tired and losing energy, but then the question becomes, how does that happen? Can we imagine a laboratory experiment where we could observe the tiring of light? Like, could we set up a mirror relay, perhaps, where light is traveling and we can somehow observe the wavelength change across a great deal of relays across mirrors? Maybe. You know, I've discussed some of these ideas with different cosmologists, and it seems like there needs to be some sort of brilliant experiment that's actually able to measure how light becomes red across distance. But these distances are enormous. These really high redshifts are at distances of tens of billions of light years away. I mean, just unimaginable distances. So maybe it's something that just isn't evidenced until you get really, really far away. So next time, let's talk about those active galactic nuclei, and we will start working towards the cosmic microwave background and start looking at different cosmological futures as well. Remember, no class Tuesday other than the one I'm going to upload to YouTube, and you guys will respond to on Flipgrid. But I will see you guys next Thursday, and yeah, try to stay warm, stay dry. Have a good weekend.